In the fascinating world of physics, the behavior of light and energy has long been a subject of exploration. Today, we dive into Chapter 3 of Yaldon Theory, uncovering the phenomena of light as it propagates through slits, interacts with surfaces, and influences our understanding of optics and energy transfer more realistically by using Newtonian physics, which is well established. This theory has the capability to explain these phenomena mathematically. Light is all around us, shaping how we see and experience the world. But have you ever wondered how light behaves when it passes through different substances? In this video, we'll explore the fascinating journey of light through refraction, reflection, diffraction, and even polarization. When light moves from one transparent material to another, like air to water or glass, it changes speed and bends. This bending is called refraction. The amount of bending depends on the difference in the size of the molecules of the mediums that the light travels between. If the angle of incidence for the light is large enough, it doesn't pass through, but instead reflects entirely inside the material. This is called total internal reflection, a principle used in fiber optic cables to transmit data as light signals. Same principle is true for the groups of particles that form the electric current when it conducted by the copper wire. When light passes through a prism, it splits into different colors. Due to the molecules of the prism that near to the corners will not be under equal force from the bombardment of the Yaldon particles. For more details, please read the book, The Yaldon Particle Theory. When light encounters an edge or passes through a narrow opening, it spreads out, due to the molecules on the surface of the edge vibrating vertically. This is diffraction. If multiple slits are used, the interference pattern will happen. Since the model of the light that's suggested by the Yaldon particle theory represents the duality of the light. The molecular structure of polarized materials is rectangular. As a result, the emitted, propagated groups of light will also take on a rectangular shape. Light easily enters materials like glass, but heat energy, infrared radiation, gets trapped because glass is a good conductor for visible light, but not for infrared rays. This is the greenhouse effect, and explains why cars parked in the sun get so hot. Did you know that light and electricity share similarities? Just like light rays move in an organized pattern, electric currents travel through conductors in propagated rays as a consecutive groups of Yaldons. Understanding this helps in developing technologies like lasers and electronic circuits. Light is more than just what we see. It's a realistic explanation that drives technology and nature alike. From refraction and reflection to diffraction and polarization, these principles help us understand and harness the power of light in everyday life.